In coding, libraries make developers' lives easier, sparing them thousands of lines of code while also increasing performance and security. Geometry Labs has released the lattice-algebra library to bring a high-performance cryptographic library to developers interested in using post-quantum cryptography in blockchain and other applications. Find out more about the future applications of this library in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Rethinking, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. So today's a bit of a first for Post-Quantum World. We're having 3 guests on at the same time. So we'll see if we can do the best we can to detangle this for the listener. So first of all, we're welcoming back our very first guest ever. That's Michael Strike, Director of Outreach at the QRL. So Michael, if you want to say hello for a second.
Hello for a second. Is this working?
Oh, there you go. Right. Yeah, so now you know his voice. And we have Mitchell Krawiec-Thayer. He's the President and Chief Scientist at Geometry Labs. Hey, Mitchell.
Nice to meet you.
And we have Brandon Goodell, Senior Cryptographer and Blockchain Architect at Geometry Labs.
Howdy, everybody.
All right, so that's our team here, and we're all here to discuss quite an intense topic. So we'll move into this slowly. Basically, we're going to be looking at what we can do to expand the reach of post-quantum cryptography and how it could be implemented in other solutions. And if you recall, we had Michael on to talk about the QRL. So I'm going to let him give a little recap of what the QRL is for some of you who might not have heard the first episode.
Yeah, so the quantum resistant ledger is a native blockchain that was purpose built to be from the ground up to be quantum secure. As many of the viewers know, the blockchain's immutability is one of its greatest features, but also could be also looked at as a bit of a crutch in that old addressing schemes never really go away. So we're purpose built. We are built off an NIST XMSS recommended signature-based hash scheme. So our signature scheme uses cryptographic hash functions instead of elliptical curve cryptography. So we've been running for, I think, about 3 years with about 100% uptime. So if you have any questions, you're welcome to reach out to me, info@theqrl.org, or visit us on www.theqrl.org. Thanks, Konstantinos.
Yeah. And as he mentioned, ECC, that's susceptible to Shor's algorithm. And this introduces a whole world of quantum cryptographic attacks. And the estimate on how many qubits you need to start attacking blockchain, it's not really that large. It's 2,500 logical qubits. We still have a ways to go, and we have to figure out what logical qubits really mean, how many you need to get there. There are some new technologies coming where qubits are getting better and better. So it might be that you only need 2,500 qubits, period. So we'll see how that works out in the coming years.
Or 20 million noisy.
Or 20 million noisy, exactly. So, and there are some exciting announcements coming, things you probably will hear on this show too. So we're not sure yet, but that could only be a handful of years away. So we have to start preparing. And now recently, so QRL is in partnership with Geometry Labs, and they were able to announce the release of something called the lattice-algebra cryptographic library on Github. And I think maybe we could start with Mitchell, if you want to give a high level of what that is.
Yeah, sure. So, we've been very focused on making sure that practical post-quantum crypto is ready before quantum computers are ready to practically break current crypto. And so what we've been working on for the last couple of months is releasing some free and open source software that is designed with the kind of mathematical primitives to start building a variety of solutions for that. And so it's a... Can I turn it over to Brandon for the more detailed
Sure, absolutely.
explanation?
Yeah, you guys could feel free to hand back and forth. I know you work together closely, so
Sure.
Okay.
Yeah. Like Konstantinos mentioned, my name is Brandon Goodell. I have a PhD in mathematics, and now I blow all my time on cryptography. Um, so the interesting thing about the lattice algebra library is sort of a data representation issue. And who said it just a minute ago? Everybody in their life needs data processing.
That was Michael.
Yeah, that was Michael.
Yeah.
Just right before we started, he said something like that. Um, so here's what's really interesting about lattice algebra is that, at least one of the interesting things for me, lattice cryptography, lattice-based cryptography, it all boils down to a bunch of linear algebra. And when you hear the term linear algebra, if you have any sort of experience from university studies or even like the internet over the past couple of years, there's so much machine learning possibilities out there. There's data representation and data mining opportunities out there. And one of the first things that you do in a linear algebra class is you learn how to represent that data optimally so that you can perform computations on it very efficiently and you don't waste a lot of computation time. If you think about it, like multiplying two polynomials together, foiling it out, it takes forever because you have to like do all of the different cross terms. But if you can represent those polynomials in a nice optimal way, then you can do polynomial multiplication very quickly. And this is called like the number theoretic transform. And so the lattice algebra library handles these fundamental mathematical objects like polynomials in a way that is safe because the timing that it takes to run an algorithm like a computation on it is constant time. But it's also actually implementing this strange world of linear algebra with polynomials. And there's actually a weird analog in real life, in fact, but in biology, to how these computations are handled. And this is something that you learn in like a neuroscience class, but when your ear hears information from the surrounding environment, it takes a sound wave in. Your nervous system, before that information even hits your brain, it does a Fourier decomposition, which essentially just like describes the sound wave as frequency instead of amplitude over time. It looks at like frequencies and amplitudes. Excuse me. Instead of representing things in the time domain, things evolving over time, you represent things in the frequency domain. So you don't necessarily look at how long a sound spike lasts, but you look at like what frequencies were present in that sound file. And this is a really optimal way of representing the data so that you can do a lot of sound processing on it. And in fact, the human eye does a similar thing. You do a sort of wavelet decomposition on the information that comes from your eye before it even hits your brain, and it represents that information optimally so that you can do computations on it very efficiently. And that's basically what our library does. It takes these keys, these polynomials that are hard to deal with and are not represented optimally, and it represents them optimally, and then it does all your signature algorithms and everything, and then it pulls it back to the polynomial world. And when it does that, it's like going through a mathematical time warp, or like a hole in space where you like pop a wormhole where you pop in one area and then you pop out another area. It's kind of magic. And so the library is basically designed to handle all this mathematical cryptography stuff as optimally as possible in a safe way.
And you want it to become
to give a,
I was going to say, you want it to become a new kind of hidden layer that people don't have to worry about.
Yeah, sort of like right now, if you're programming, you got to use integers or you got to use floating point numbers, right? These are fundamental types inside the computer. And basically what we've done is we've taken these cryptographic objects, polynomials, and vectors of polynomials, and we've turned them into a type in Python so that you can just add them together and multiply them together as naturally as you would an integer in Python. And that makes programming cryptographic protocols like a snap, like 100 lines, 20 lines, something like that for a good signature algorithm. And all you're doing is you're putting all of the security and development problems on the underlying libraries like the Shake 256 expandable output function, or other issues. That way you don't have to worry about any implementation risks of like some developer coming in, trying to program up some cryptographic protocol, screwing something up, and then as a consequence producing something that's insecure. We want to be able to eliminate that as much as possible.
Yeah, anything resembling homebrew is always a bad idea. And Mitchell, you were going to say something?
I was going to follow up the comment about.
Oh, okay. Yeah, we could just cut that. That's fine.
Or I guess yeah. Sorry, I can. I'm assuming we're going to cut this a little bit out. What I was going to comment was a concrete example of, say, we have two polynomials we want to add, with all the stuff being under the hood. For the top level programmer, they can just have the theory paper open on their left monitor, have their IDE open on the right monitor, and literally just kind of grab the theory stuff out. We've actually done some side-by-side comparisons of the Python code and the theory papers, and they're very similar. And so in addition to taking that coding complexity out, that attack surface out, and all of the complications that come with coding that up, we now make it more accessible for cryptographers to kind of interact with these things and not just have to go deep in the weeds coding up critical mathematics before that. So we hope that this is a massive productivity tool for people developing cryptography applications, that they can just fast forward half or 2/3 of the way through the project, have all those primitives at their disposal, and then just kind of like build out the high level pieces.
Yeah, there's this really common thing in cryptography where everybody tends to just program up their library that does exactly the protocol that they were trying to code up, and then they go to another protocol and they have to recreate an enormous amount of their infrastructure because they're just coding up each protocol on its own. And there's a good reason to code up each protocol on its own without having like a common library underneath them, which is that you're centralizing, you might be centralizing a development risk or some sort of insecurity in the code. You're centralizing it into a single location that's being referenced by multiple deals. So that's very problematic in the development world. However, when you have to recreate your infrastructure over and over and over again, what you end up with is people programming the number theoretic transform uniquely for each instance of each cryptographic protocol that they are working with, and it's a slow process. By typing everything out this way and turning things into types like integers, the idea is to make a productivity tool that just like you can take the math and put it into Python and hit go.
So without being a programmer myself, basically, and for everyone else that might be watching this that might not be an algebraic expert or a programmer, essentially what we're talking about is a modular approach to being able to build out provably secure quantum secure code without having to be an expert in each of the respective fields that would be required to do so. That's what I heard. That's the way I understand the library to be. Konstantinos, if you don't mind, I got a question or two.
And I was going to ask you too, to just explain the biggest thing that you're hoping this brings to QRL.
I can do that. Really what the goal of this, I think, where the partnership, the goal here is to, as part of our educational and research arm, we are trying to take novel approaches to solving problems that people have thought about, but maybe don't have solutions for, and being able to provide essentially what some might consider a software development kit or a modular architecture to being able to build their own applications. I think that's really powerful because, to me, it's a bit like a platform like an operating system or like a smartphone. You don't have to know how an OLED display works. You don't have to know how all the hardware works. You don't have to be an RF expert. You don't have to build the phone. You already have the modules there. You can just call them and get they do one thing. From my understanding, they do one thing, and they do that one thing really, really well, right? And deterministically. So what we're trying to do is essentially educate and empower everyone else to be able to build their own quantum secure applications and services, and some of those in the future, based on the life cycle of how I myself and others view the QRL project, some of those would be on chain on the native QRL blockchain, and there's not a lot of players in this space, so we're in some ways leading some areas of this space. The space will grow, and I see our, for lack of a better word, knowledge market share growing as well as we put more and more time into these. But I was going to ask Mitchell and Brandon, with all of you've been talking about these primitives and algebra. I think one of the things I didn't hear said is these enable a lot of features that the QRL project will be able to take care of, that will handle some of the problems moving forward. For example, like scalability with signature aggregation. I know you guys have built in some built out lattice-based proof of stake signatures, plus the aggregation that goes onto that, so that the information can actually be brought to scale. If you've got 10,000 validators. One of the questions and I'll let either one of you talk about this. What new capabilities, like the lattice-based signatures, proof of stake, consensus, Lightning Network payments, what are those going to be able to bring this code? What functions are those going to be able to bring in a post-quantum secure world for people that might want to implement them? And the other question I personally had, I think, was the signature aggregation piece is interesting to me. I wonder if someone could explain what the costs are. And what the costs are in aggregating all of the signatures together. I'm assuming it's just a CPU cost in order to do that upfront, and then on the back end you save space natively on the chain. But take it away. Either one.
I got it. I can do this one. Mitchell, feel free to interrupt me at any moment. So one of the cool things that we can do with lattice algebra. By the way, lattice algebra is the name of the repo, or the library that we put out, right? So throughout this conversation, it's possible that mathematically inclined people are going to be like, lattice algebra, what do you mean by it? I mean the software package. One of the cool things that we can do with the lattice algebra library is implement signature schemes very quickly and easily, as long as they don't have key distributions that are a little wonky. And that is a technical term, but
I use it all the time.
Right? It's a very useful technical term. So one of the cool things that you can do is aggregate signatures. So a Schnorr signature is basically a linear combination of two keys. You have a key X and a key Y. You hash a message to get a challenge C, and you compute X plus CY. And that's basically the Schnorr signature. In order to verify it, you then use that as a secret key, and you put it through whatever secret key to public key map you have access to. So in the discrete logarithm world, you exponentiate. You go G to the X plus CY. On the other hand, in the lattice world, you take a dot product. It's like linear algebra from college, where you just take a dot product between X plus CY and this public challenge element. And there's this white paper that was published by Dan Bonet and Sam Kim a couple of years ago. And I shouldn't say published because it's a white paper. It's not been peer reviewed. It's just been on the internet for a couple of years as a preprint. And it has an interesting non-interactive aggregate signature scheme in it that's sort of like Schnorr-like from the discrete log world. And it sort of has the same sort of algebraic structure to it. And in fact, if you look at things from the correct perspective, they're in fact just two instantiations of the same scheme, Schnorr and this Bonet and Kim scheme. But they go ahead and they prove in this paper that those signatures can be aggregated. And for years, the Schnorr signature aggregation thing has sort of been like a urban legend. Like everybody says that it can be done, but nobody's really sat down and proven it, written up a security model. And they did that in this paper. And that's like the discrete log world, but then they carried it over to the lattice-based world, and they have this kind of interesting aggregate signature scheme. And when we were reading through it, I noticed that the parameter selection sections seemed to be thrown in there last minute. And I don't want to criticize Bona and Kim at all, because it's not been peer reviewed, right? It's not been published. They just posted something that they had started to work on the internet, and I picked it up, and then I started working on it from there. As a consequence, we can do aggregated signatures. So the way aggregated signatures work is instead of having to check each signature individually, the goal is to check some smaller structure than all of them, right? Because I can aggregate signatures just by stacking them, and then I just check each one. And I can call that an aggregate signature. Congratulations. But I didn't save any space or time or anything, right? I just listed them in order. So the goal is to, instead of taking an O of n amount of time or amount of space to describe an aggregate signature, the goal is to describe it in some sublinear size, like a logarithmic size. And so the aggregate signature scheme is supposed to take n keys and a log of n space in a signature size. Whereas a normal signature scheme, if it's a one-time signature scheme, requires n keys and n signatures. So you're taking all of the weight from all of the signatures and you're chopping it down to just a single signature. So instead of having to post 50 keys and then 50 signatures, you just post 50 keys and one signature, which is great. And you want to be able to merge these signatures together in a way that doesn't require interaction between all the signers, so that when people announce transactions on the network, they can aggregate those signatures together without interaction from the original signers. And then the stakers can make their signatures, and they can aggregate those together and get 64 signatures or something like that, all in the space of one signature. Of course, the size of the signature and the size of the keys really determines how efficient the whole setup is. But it looks like we have it. Parameter selection is still going on, and I don't want to get in the weeds on that. But we have had some very, very positive movement in the parameter selection department, and we're pretty sure that we have signatures that are at least competitive with the NIST competitor scheme, crystals dilithium. If you compare just stacking n signatures and n keys, which is sort of unfair because crystals dilithium keys can be reused multiple times, and our scheme is a one-time signature scheme. But the idea is basically to take all of the weight that you would have to put on the blockchain and that's in signatures and just basically throw out most of it, and in a way that's still verifiable. And that's a fun little question in the whole.
So the interesting part of that, of what you said, is it's a bit like a hash. You're going to be able to agree on that aggregated signatures string, but not necessarily not extrapolate it at a point in the future not extrapolate it based on a point in the past of what all those signatures were, right? Is that correct?
Yeah, it's not. You
can't derive them or get them back if you were to go back in time.
It's not like a zip. It's not like a zip file sort of thing where you're like compressing them and then you can expand them back again. It's a compression only, right? So you take all of these signatures, you map it down to a single small signature, and everybody can check that small signature against the keys and the messages and make sure that that thing is a valid signature in a way that's
And then all you need is consensus, and then you can just move on in life. Go to the next block. I'm sorry, Mitchell, I think you were going to say something.
Oh, yeah, no, that's a good segue. I was going to zoom out kind of to the applications for this. So one of them, of course, is proof of stake consensus mechanisms. And because of the way these signatures are structured, we could actually aggregate transaction signatures into other block signatures if they're using the same underlying math. Then you can imagine that kind of as like a tool for building things starts to look not only like proof of stake consensus or aggregating signatures, you could use that for on-chain governance, right? Or for DAOs. If you have, you want a K of N or M of N multi-signature wallet, right? So there's 10 parties, and if any 6 of them will say arbitrarily sign a transaction, we want that to be valid. So that could look like anything like multi-sig QRL transactions to on-chain governance, anything like that, where you want to keep your footprint small on-chain, do that work off-chain, and then upload something small for verification. And then kind of branching out beyond the signature aggregation piece, the other extensions that we are building with the lattice-algebra library include adapter signatures, which I'll gloss over the technical piece. The applications are cross-chain atomic swaps, which are these trustless, decentralized, where like we could swap between QRL and Bitcoin or QRL Ethereum. Brandon figured out a way to trade secrets between like the lattice side and the elliptic curve side, which is what these other currencies use.
And I haven't proven it secure, but I think.
Okay, we'll put what we think.
We'll cut that part out.
And then the other
yeah.
and then the other application is payment channels. So this is within the QRL ecosystem, starting to build something that looks like the Bitcoin Lightning Network, where you can now have a second layer, move a lot of traffic off the base layer, and only settle onto that when you need to open or close the channel. And then there's some even further applications out there that we're not currently building on the roadmap, but a variety of zero-knowledge arguments, which, Brandon, do you know off the top of your head some of the like cookbook parameters?
I don't know much about parameters from that. With
not parameters,
with small modifications to so basically all the signature schemes that we've described so far, the aggregated signature scheme, the adapter signature scheme, these are both doable in a very small number of lines of code. With our lattice-algebra library.
With the lattice-algebra
specifically,
library.
I can in fact open it up really quick, and just because I'm curious. Then, in addition to that, there's certain math papers out there, or cryptography papers, that propose like a whole ecology of crypto protocols. Simple things like accumulators, right? Like simple things like commitments and range proofs, right? Very, very sort of like basic cryptographic tools that haven't really existed in the lattice world for a long time, because before now, lattices were way too inefficient. Lattice cryptography was too large. It was thought to be too large. It turns out we can actually get lattice cryptography down pretty small. If you look at like the Swift compression function, which is based Swift with 2 Fs. That's based on the fast Fourier transform, and that's what I was mentioning earlier about the number theoretic transform and the human eye and the human ear. Mm-hmm. Their parameters are super, super small for that. Of course, all they're trying to build is a function that's collision resistant. They don't have all of these extra properties like unforgeability and stuff like that their signature schemes have to deal with. So their parameters are made super small. And so anyway, until recently, the lattice-algebra lattice cryptography based schemes tended to be too inefficient. With the lattice-algebra library, we hope to modify that, and with access to like the whole zoo of cryptography protocols that have come out over the past 5 or 6 years, it's been like a renaissance in cryptography. The idea is to be able to start to rapidly prototype things like an accumulator scheme or a signed commitment scheme or a blind signature scheme or something like that. Just rapidly prototype these things using our underlying lattice-algebra library. I'm pretty sure I answered that question.
I wanted to pull us out a moment into this concept of proof of stake. I think it's incredibly important. People have argued that that's what will save the world, literally, when you're talking about energy consumption and everything. So first of all, maybe, Michael, you want to talk a little bit about proof of stake, and then we could talk about how the lattice-algebra library will help enable that for both QRL and maybe other things like Ethereum.
I almost don't know if I should, because proof of stake versus proof of work versus proof of X is a very tribalistic, contentious and tribalistic, and spears do come out.
Well,
but I'm going to give my opinion, but with the prefix of these are my opinions, and they may not be representative of the entire team. I think that I like both proof of work and proof of stake. I think that there is something novel about being able to store energy, actual stored energy. I like the proof of work system, which solved the Byzantine fault tolerance issue, right? There's a lot of conversation, which I think we were alluding to, Konstantinos, about proof of work not necessarily being green, and there's some there are some jurisdictions that are now banning Bitcoin mining without, as if they can't at least prove that they're green by either a running direct green or showing proof of green credits, right? At the end of the day, I'm trying not to make predictions here, but oh well, let's just do it anyways.
Gun to the head.
Here's how I see Bitcoin as a bit like the world reserve currency, in that except back when the US dollar was backed by gold. Back when coins were actually made of silver pre-1965, and back on the gold system pre-Bretton Woods, you could exchange your dollars for gold, and you could exchange your gold for dollars, and you would get the dollars, and that dollar was essentially a piece of paper that was worth something. And that it was worth something because it took actual work. There was blood and sweat and gears that took to be able to get that out of the earth. And to me, that's something that can't be gamed. At the end of the day, I'm a bit of a purist, black or white thinker. And, there's arguments against proof of stake, in that, okay, so I just put this here, I don't do anything, and the rich get richer. You'll hear narratives like that. I think there's a place for both of them. And at the end of the day, what I see is proof of stake, proof of space, proof of LMNOP, all being pegged to a proof of work system, in this case, likely Bitcoin. Now, this, of course, doesn't take into consideration the quantum threat, because the QRL acts as your quantum insurance policy against, proof of stake and proof of work, and 99.9% of other blockchains that are dependent on elliptical curve cryptography and susceptible to Shor's algorithm and a sufficiently powerful quantum computer. But I am of the opinion that all of the proof of X's complement proof of work, because there's something ideological about having to actually do something in order to get something. Because if in the history of money, anytime you don't have to actually do something to get something, that system itself always seemed to evolve and take form in a bit of what I would probably best describe as cycle of empire theory, in the collapse of the Roman Empire eventually. And this takes a long time. So I probably went off on 2 or 3 different tangents there, but that's my opinion.
So how does, so I guess either Brandon or Mitchell, how would lattice algebra help move to at least a partial proof of stake system?
Dude, I have so much to say.
I know, yeah.
And
I stopped myself.
Well, you could start with what you want to say.
And then good things.
Yeah, you could just touch on how this...
Be kind.
Mitchell, do you want to go?
Oh, I can briefly comment that I actually am very interested in a variety of consensus mechanisms. I think it's one piece of this type of framework that's actually in many ways orthogonal, right? Like you can take a given currency with various features, whether they're privacy or smart contracting, whatever, and you can swap out proof of work, proof of stake, right? So it's kind of this orthogonal piece. I really like Nakamoto consensus and proof of work's properties, right? Where you have this notion of the longest chain, and evidence of what went into that. Also, environmentalism is a very real concern, and having the best money doesn't matter if I don't have air to breathe. So I also am very interested in seeing alternatives to that. Proof of stake is definitely one of the ones that's, I would say, more developed and battle tested. And so, of course, we're putting some time there. Personally, I like proof of space or proof of space time. I think it has a lot of the Nakamoto consensus-esque properties where it can run on commercial hardware. there is physically showing, in this case, it's, bits of storage rather than electrons of hashing. But you end up with similar properties. You can get heavier chains, lighter chains, all of that. But that's maybe a different story. Brandon, what were your thoughts?
I'm super sympathetic with Michael's perspectives and yours also. Environmentalism is deeply important to me. Unfortunately, so there's this really habitual thing that happens in the Silicon Valley world, and this is a criticism of that particular culture, but it happens almost everywhere, where people are like, "Oh, I can sell you a product that does X, Y, and Z," and it turns out, after decades of selling this product that does X, Y, and Z, somebody can mathematically prove that either you can have X and Y, or Y and Z, or X and Z, but you can't have all three at the same time. And so there's these theorems in mathematics called impossibility theorems that are basically 2 of 3 theorems that say, okay, you can have any 2 of these 3 properties, but you can't have all 3. And oftentimes reasonable sets of assumptions come in 3s, and reasonable sets of assumptions come in 3s that are mutually exclusive in this way. And so I personally have read a variety of proof of stake papers that are rather critical of the underlying assumptions that lead to the security argument. For example, there's this paper called Rethinking Large-Scale Consensus by Elaine Shih, or Shy, I believe it's she. I've not met her or seen her speak, actually. But that paper proves that under some reasonable set of assumptions, like you want people to be able to join into your staking system at arbitrarily long periods of time in the future, right? You have late spawning, so people can jump in sometime after the Genesis block and start staking. That assumption, unfortunately, is contradictory with some other reasonable assumptions. And so it seems to me that proof of stake is not provably secure under reasonable assumptions. Having said that, you can tie stake together with work in alternating chains, and that can offload some of the energy cost of proof of work onto proof of stake. And then you can use the proof of work's security as like a foundation for the proof of stake for a certain number of blocks. And you can still gain those security claims. I really like proof of space. I really like proof of time when they are described in the correct context, or rather, like, I don't want to say the correct context because that means that there might be something wrong out there, but like there's a certain context that's like the real world model of how we want to use these things. And I like proof of space for those things. But Michael, you mentioned something that reminded me of a book called 1,000 Years of Nonlinear History, where they talk about how every single time humanity basically gains access to a new energy source, our whole society crystallizes. So like when we went through the agricultural revolution, all of a sudden we could collect all the solar energy that was stored inside of these plants, and all of a sudden we crystallized into like the agricultural revolution. And then when we like started burning coal for energy, we crystallized during the industrial revolution into a different form of society. And I'm kind of intrigued by cryptocurrency in part as like sort of like a picture of that process, because what you're seeing is like people wanting to go back onto something like the gold standard, but we don't want to like make our money based on blood, sweat, and tears and people like dying in the ground, right? And it's an interesting question, but overall, I think that there are some really interesting ways to move forward to mitigate energy costs of proof of work. Unfortunately, I think proof of stake is let's say that it's based on reasonable but contradictory assumptions.
It's human behavior. Proof of stake, really, the consensus is really based on, at the end of the day, if you look at things completely objectively, okay, it's really based on expected human behavior based on game theory, right? If I have a large stake and I control a lot of that portion of consensus, there's a strong game theory in human nature that says that I'm going to want to make sure that the things that I'm doing are in the best interest of the network. And our project is moving towards proof of stake, and I agree with that. But like I said, I think I liked all the things you said, Brandon and Mitchell, both of you. But at the same time, proof of work, it's really more, I see it more mathematically pure in that it doesn't depend on biological or subjective variability. It really just depends on math, and math is one of the most objective.
Depends on physical work. It's the number of electrons that have been moved from point A to point B, right? Like that's what proof of work is all about. And when you're starting to talk about like the ledger as recording that expenditure of energy, you can't fake it, right? But you could, with proof of stake, you have the stake.
But you're also subject to running your other human behavior, right? If a government imposes lockdowns because of power consumption, or if a region can't support the machinery, then you're subject to all that too. So that's why some kind of hybrid approach there seems to be the best way. Good amount of work, good amount of stake, and then everyone's kind of covered.
Well, and that's true, but at the same time, someone else will pick up the slack. And is that government doing a disservice to its constituents? Yeah. Mm-hmm. I mean that. Oh, go ahead.
Sorry, Michael. No. Dude, I agree with you completely. So one of the problems with the whole cryptocurrency world is that whatever you base your consensus mechanism on tends to undergo hyperinflation. So if you have proof of work, then you have hyperinflation of CPUs and GPUs and ASICs that end up becoming really cheap to produce in a couple of years, and they're in large numbers because work is easy and it is profitable. On the other hand, if you start doing something like proof of space, then hard drives undergo this hyperinflation, and all of a sudden Amazon can like hammer out any consensus they like, and they own the world, right? And so whatever consensus mechanism you base your economy on, it sort of has to go through this hyperinflation period. And if we do work, then it's hyperinflation of work and like work devices. And if you base it on disk space, then it's going to be disk space. And I don't know what the solution is there for sustainability, because it really, really seems like the paperclip machine that's designed to build more paperclips.
And to that, in case in point, I remember when Chia came out.
I was just about to mention that.
Were you about to mention that? What happened, Konstantinos? Help me out here. What happened to hard drive prices?
Chia, for those who don't know,
for a 16 terabyte
it's
or
kind of funny
because
the creator of BitTorrent essentially said, "Hey, be a great proof of something. How about your hard drive space? The more you have, then you can farm." He called it farming. So, now that song's stuck in my head. Anyway, so you've got this situation where you're farming, you're using hard drives, and it's kind of funny because BitTorrent always was sort of a hard drive thief, wasn't it? You start downloading movies and music, and all of a sudden your hard drive's full. So I guess you kept kind of going with the same principle. But yeah, prices go up, and that affects the whole thing. So to kind of tie this all together, I just would love like a high level of, let's say, 2 or 3 of these moves and future switches and technologies that you think lattice algebra can help implement to basically kind of bring it all home for the listener. Yeah.
Oh, okay. Super easy. Aggregate signatures are going to make it so that the cost of staking is about the cost of, hopefully, a single crystals dilithium signature, which is like 2 kilobytes. Which or like 5 kilobytes. That'd be super fantastic. Being able to take all of the stake stuff and non-interactively aggregate it into a very small amount of block space, comparatively small. Fantastic. There's a technique called secure fountain architecture that we're looking into right now. That's based on mathematical coding theory and using the hash chain of the blockchain, the chain of hashes, as an authentication structure to run this very simple coding theory based algorithm so that you can basically shard your data. So long term, local nodes can start forgetting sections of the blockchain that have become inactive, and they tend to not even need to like track when that happens. It just happens naturally that they stop accessing that part of the blockchain, and then they end up storing 1/100th of that part of the blockchain, but in a verifiable way, so that if later somebody ends up spending out of that section of the blockchain, they can still reconstruct the entire thing. Super fantastic. So it's like, unlike the aggregate signatures, which compress things down only, this method is like a peeling decoder method where everybody stores 1/100th of the blockchain, and then you talk to 100 different nodes, and then you compare and you can peel off the layers of the blockchain that you need and use the hash chain to make sure that nobody's lying. It's super cool. So long term, you can like reduce the total percentage of local storage space for nodes. We're going to be able to aggregate signatures so that the overall blockchain is smaller. That hopefully should enable some sort of hybrid stake work animal that's secure. And if not that, if the QRL community really wants stake, then hopefully we'll be able to do, like, my goal is that each block just consists of the output keys and a single signature. That's it. That's what I want. Oh, and like a header and hashes and stuff like that.
But does everything.
Basically just
doesn't sacrifice any usability or use cases.
Yeah.
That would be ideal.
Yeah.
And post-quantum.
And let's, let's remember that right now, in the case of Ethereum, gas prices are through the roof, worse than like the gas you put in your cars.
Yeah.
And any of these moves would help take, the pressure off of that.
I should point out that secure fountain architecture stuff is not related to the lattice algebra library. It's a completely blockchain agnostic, different animal that can just be layered on top of any blockchain that's out there right now. It's really cool.
Consensus uTorrent storm or
swarm.
Sorry, swarm is the word.
Yeah. That's basically
a lot of BitTorrent. Yeah,
that's
a lot of
that's
BitTorrent feeling things are coming back to move into the blockchain world. You could see it. Yes.
I
hope we're making Bram proud.
So, I guess with that we'll wrap up, and good luck on the project. And I have a feeling in this episode, a lot of people are going to be listening to the section at the end called Coherence, where I summarize what we talked about. I have a feeling this one they're going to tune in for that part. So thanks very much, guys. I really appreciate it.
Excellent.
Thank you.
Thank you.
Yeah. Thank you guys so much.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. The Quantum Resistant Ledger, or QRL, is a purpose-built blockchain designed to be post-quantum safe. Check out our first episode for more on the project. Recently, the QRL partnered with Geometry Labs to release lattice-algebra. This is a cryptographic library available now on Github. Linear algebra comes up a lot in quantum algorithms. It comes up here in this cryptographic approach too. The lattice-algebra library handles fundamental mathematical objects like polynomials and vectors in an optimal, safe way to aid cryptographic solutions. Working with these objects as types becomes almost as easy as multiplying integers when writing code in Python. The work gets passed on to the lattice-algebra library underneath. Libraries minimize coding time and reduce security risks for mistakes when writing everything from scratch. With primitives at their disposal, coders can start cryptographic projects way ahead of the post-quantum cryptography, or PQC, game. In this case, the hope is to build post-quantum secure code quickly. Developers don't need to be experts in the PQC types underneath. Also, the hope is these primitives will aid scalability. The lattice algebra library can be used to implement a Schnorr-like one-time signature scheme. This could allow for zero-knowledge proofs and signature aggregation, which is useful for PQC wallets and blockchain. There's a lot of weight on the blockchain today associated with storing multiple signatures. Lattice algebra could reduce this. For example, instead of posting 50 keys and 50 signatures, you can have 50 keys and one signature. And like a hash, this solution can't be reversed. The team is also working on cross-chain atomic swaps to trade secrets between blockchains. Swap between, say, QRL and Ethereum in a trustless way. It seems there are many zero-knowledge approaches possible. The team is thinking of this library as opening up a cryptographic renaissance of applications in the future. Lattice algebra could potentially aid proof-of-stake solutions with lattice-based signatures that take up a minuscule amount of space, maybe sub 5 kilobytes. Proof-of-stake is an almost political area of blockchain, so we'll leave it at that. Another promising future application the team is interested in working on is hashing parts of the blockchain in a way to enable sharding. This means local nodes can forget inactive parts of the blockchain, storing about 1% of it only. Think of the space saving there. That does it for this episode. Thanks to my guests Mitchell Krawiec-Thayer and Brandon Goodell from Geometry Labs, and Michael Strike from the QRL for joining. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at ConstantHacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.